In this video we're going to introduce the term the equilibrium constant. The equilibrium constant is a number that gives us some indication of that position of equilibrium. Does it lie to the right? Does it lie to the left? It's going to give us some indication of where our equilibrium lies. It's not a universal constant like the speed of light. It varies for every reaction, so it's a constant for a particular reaction at a particular temperature. So that's in terms of things that physicists might look at, not very constant at all, but it's a constant for a particular reaction at a particular temperature. So there are lots and lots of equilibrium constants depending on the reaction you're looking at and the temperature at which you're studying it. It's measured in terms of concentrations, and that's what the little c next to the capital K is for. So we're using square brackets around our reactants to indicate that we're using concentrations. And for an equilibrium, it is the concentrations of the products over the concentrations of the reactants. So on the top line we've got the products. So it's a measure really of how quickly the products are being produced, so how much products we've got at equilibrium, over the reactants, their concentrations. And you'll notice that their powers at the top here are to do with their stoichiometric coefficients, the number of moles in the balanced equation. So the number of moles in the balanced equation. We're going to have a go at writing those in a minute. So what's the significance of the value? If the number, remembering that it's products over reactants, let's just write that. Remember, it's concentration of products over concentration of reactants, and it's like a little ratio. If that number is less than 1, what does that tell us about that fraction? Is it a top-heavy fraction or a bottom-heavy fraction? So when you look at a fraction, the answer is less than 1, that means it's a bottom-heavy fraction. So we've got more reactants than products. Equilibrium lies to the which side? So equilibrium lies to the left. More reactants. Which means that if it's to the right, greater than 1, we're going to have a lot more products. And when we have more on the top line, we get a top-heavy fraction. Kc is equal to 1, then equilibrium would be smack bang in the middle. I don't know an example where that actually happens, so we could even put this in brackets, because that is very unlikely. Now, because the expression for Kc varies depending on the reaction, then the units for Kc are going to vary depending on the reaction. So let's have a look at an example. So here's an example of an equilibrium. If we wanted to write the Kc expression, we would write Kc equals, so it's a capital K for equilibrium constant. The little c tells us about concentration, because next year you're going to be introduced to another one of these with a P for pressure, and one with an A to do with acids. It's going to be the products. So on the top of our fraction we want the products. So the product is only one thing, NO2. It has to be concentration. So these must be squared brackets. If they're not squared, the exam board are going to knock you marks off. And it's going to be raised to the number of moles. So why is that? Why is it raised to the number of moles? Well, it's just a shorthand, isn't it? Because on the top line, anything that was added in this expression, we'll have a look at another example in a second, is now becoming multiplied in this equilibrium expression, and NO2 with a 2 in front of it just means NO2 add NO2. So NO2 times NO2 now becomes NO2 squared, and on the bottom line it's N2O4. There's only one of those, so it's just N2O4. So that's my expression. How could we work out the units? So we know the units of concentration. So we can use that to work this out. So we've got a concentration term squared on the top line, and we've got concentration units on the bottom line. Now in maths, we've been practicing in our skills what that means in terms of algebra. That means that we've just got C, because we've got C squared divided by C, that's C to the 2 minus 1, that's just a C. What are the units of C? They are moles dm minus 3. Let's have a look at another few examples and we'll see what we can do with those. So here we've got another one. Let's write our expression for Kc first. So Kc equals products. So anything that was added becomes times, and because it's about concentration, we use a square bracket. So we write that first thing out. That's called ethyl ethanoate in square brackets. And we multiply it by the concentration of water. Now notice that we don't need to put a multiplication sign in. As long as those two are next to each other, they are multiplied. There was one of each, so there's one of each on the top. And then we put the reactants on the bottom. We've got ethanoic acid, concentration, square brackets, and we've got ethanol. Again, make sure you use square brackets. And what would the units be? Well, we've got the units of concentration times by the units of concentration, divided by the units of concentration times by the units of concentration. So there are no units. Okay, remember this is not a universal constant where the units mean an awful lot. The units are just telling us about how many moles were on the top and the bottom. When there's no units, it tells us there was equal amounts on the either side of the equilibrium. So let's have a look at another one. Products, ammonia. So two ammonias means ammonia add ammonia, or in this case now it's going to be ammonia times ammonia for the mathematical expression. A nitrogen and 3 hydrogens, so H2 cubed. What would our units be? We've got concentration squared over concentration times concentration cubed. So 2 take away 4. We've got concentration units to the minus 2. Now concentration units are this, mole dm minus 3, and we've got them to the minus 2. So when there's not a number after it, we know it's a 1. So moles to the 1 to the minus 2 is moles to the minus 2. Remember that when you expand this bracket, you multiply. dm minus 3 times minus 2 is dm plus 6. So our units would be moles minus 2 dm 6. Have a go at this last one, see if you can work it out. So you should have got sulfur dioxide squared times oxygen over sulfur trioxide squared. We've got 3 lots of concentration on the top and 2 on the bottom, so we just have the units of concentration. There are many, many more of these in your study pack that you can use to practice.